Example 4. Solve the equation the square root of x minus 1 equals x squared minus 3 using Newton's method. Find the solution accurate to 3 decimal places. Before we actually start doing this problem, I'm going to write down the formula one more time, but I'm also going to add in one extra piece of information that I didn't write in the previous example. And there's a reason that I'm going to write it in this one. Okay, so first of all, here is our formula. But the other important part, which we said out loud last time, but we didn't write it down, this applies to some function that's equal to 0. So as of right now, this is in a form I can use Newton's method on. Newton's method is meant for finding roots. But all we have to do to turn this into a roots question is to just move everything to one side. So why don't we go ahead and do that? We could subtract by x squared on each side and add 3 to each side. And this gives us, what, minus x squared plus the square root of x, and minus 1 plus 3, that's just 2. And so what this means is that our function is just this minus x squared plus the square root of x plus 2. And before we can actually use Newton's method, we also need the derivative. And the derivative here is minus 2x plus 1 over 2 times the square root of x, and then plus 0. Okay. Next, let's start plugging stuff into the formula. So if we say started off with x1, right, we have x1 equals 2, then x2 is going to be equal to x1 minus f of x1 all over f prime of x1. Okay. And here in a minute, I'm going to show you how I would plug all this into my calculator. But we could find x3 here if we wanted to. And x3 we would find by using the same process, x2 minus f of x2 over f prime of x2. And let's just see what both of these were approximately equal to. x2 is about 1.89. Oh, let's fix that. 839.35. 4171. And I'm writing it out to all these decimal places for a reason. I'm going to want us to compare as we go here. And then the next one is 1.831198. 422. And if we were to go one more, x4 would be 1.831177,207. Okay. Now that we've computed x2, x3, x4, let's think about why we've stopped this process. Okay. And so what I want you to do is just from x2 to x1, I want you to notice that we kept in the same digit in the 10th place and in the 100th place. Okay, and you might notice that we actually kept that even into the fourth one. And you'll see on our calculator, if we were to go even another one further, we'd still keep that 8.3. And the idea is that as we perform Newton's method, we're getting closer and closer and closer to the actual root. Okay, so if you see that some digits are not changing from one step to the next, that means we're going to keep those decimals as we continue the process. Okay, so we know so far that we're accurate at least up to 2 decimal places. Okay. And actually, we know even more than that. If we were to maybe ignore the x2 here and just look at x3 and x4, they actually have up to 4 digits that are the same. And as what this tells us is that we have 4 digits of accuracy. We're accurate up to that 4th decimal place. And if I were to find x5, it will, we'll see this on the calculator in a minute, it will have 1.8311, and it might even have a few more numbers that are the same after that. Now that we are looking at our calculators here, let's go ahead and type in f of x and f prime of x. So for f of x, we had this minus x squared plus the square root of x plus 2. And then we had the derivative of this as well. And we'll just type that into maybe y2 here. So there's y1. y2 was minus 2x. Let me go back into my y equals here. There we go. Minus 2x plus 1 over 2 times the square root of x. There we go. Next thing we're going to do is we're going to go to the main screen. So I'm going to hit second quit. And next I'm going to type in 2 minus, because right, our x1 was the number 2. So 2 minus. And then I'm going to hit vars. I'm going to go over to y-vars. I'm going to hit enter on function and enter on y1, because y1 here was f. And then I want to divide this by f prime of 2. So remember, in y2, we typed in what f prime was. So I'm going to hit vars again, go over to y-vars, function, and this time we'll go to y2, because again, that's where our derivative was. And we'll also plug in 2 here. And so if I hit enter, this should give us that first answer we saw was 1.83 something. Well, now if I want to compute, say, x3, well, I could hit second, enter. But this time, I just want to plug in the previous answer here instead of 2. So second, and then the negative sign will give us a and s. Let's try that one more time. Oh, my calculator's just running a little slow. There we go. So we have our second answer, and I'm going to insert my subtraction sign back there. And in place of 2 again, I'm going to hit second and then the negative sign for answer. And then I'll replace that last 2. Okay, there we go. And that's going to give us x3. And you can see now, we know we at least have those 2 decimal places of accuracy. And we should just keep getting more and more decimal places of accuracy. Let's see here. So second, enter. And if I hit enter one more time, there we go. And you can see now I can see 4 decimal places of accuracy. Okay. Right? The 8311 is not going to change here now. And we could try another one, but I believe we run out of digits here for it to actually make a difference. Yeah, so it looks like it's giving us the same answer, but it's actually a little bit different. It's more than 10 digits out, so we can't see that change that's occurring here now. Now that we're done with our calculator work here, we can record our final approximation here. So we just said we needed to be accurate within 3 decimal places, and we have 4. Okay, so we'll just go ahead and write it down. X is approximately equal to 1.831.